Welcome guys to a new series. I'm super excited to get started on this one. We're designing active aero for our car. This will be applicable to any car. It'll be more applicable to lower power cars, but you can easily modify a lot of the stuff that I'm doing to fit higher power cars as well. So the first thing I'm going to go over is just kind of the diagram of how it's going to work, and then I'll start talking about some of the research that I've done so far. Here we've got the active aero system. This is the whole thing. Now this is kind of a systems diagram. It's not SysML or anything in particular. It's just kind of a guide on how I'm going to do my research and development. And so we have hardware, software, and electronics. I'll cover this more later, but feel free to pause and look at that. The hardware is what we're going to be looking at first, because we have to define what the software and electronics is going to control. And then we have the aerodynamic, structural, and mechanical components. The aerodynamic components will define how much stress and work the structural components and mechanical components have to do respectively. So the first step is the aerodynamic components, and that's what I've been doing a lot of research recently for, and what we're going to dive into today. So my objective is to have it withstand up to 150 miles per hour. That's very fast for the kind of car that I'm designing this for, a GR86. You could also use this for a Miata, an Elantra N, cars sort of in that performance class. Think of like the sub 40,000 semi-performance kind of sporty kind of cars. I'm going to be saying the word lift a lot, and I know it's kind of confusing, but when you analyze an airfoil, you analyze it for lift and drag. Now we're turning our airfoil upside down to create downforce, but I'll probably be using lift and downforce interchangeably. Just a heads up. I know that's kind of weird, but it's just the way analysis works. Everywhere it's called lift when you analyze an airfoil. So if I say lift, just think downforce. Let's get into the aerodynamic analysis that I've been doing. So whenever you look at airfoils, there is a number called a NACA number, the National... It is a Neighborhood Assistance Corporation of America number, and that means... I'm just kidding. National Advisory Committee for Aeronautics, and that is a 4 or 5 digit number that defines the shape of the airfoil. The first number means basically how much camber or curve it has. The second number defines where that curve is centered on the airfoil. And the last two numbers is a percentage of how thick the airfoil can be. So if the airfoil is 10 centimeters wide and the last two digits is 10, that means it can be 10% as thick as it is wide. So a 10 centimeter airfoil would be 1 centimeter thick if it ends in 10. So for example, if you have a 2410 airfoil, it's going to have a camber value of 2. So 2 millimeters off of the center line is what that means. So if you have a 10 centimeter wide airfoil, you have a 2 in the first number, or the first digit of the 4-digit NACA number. That's going to mean 2% of the chord length is how far off the center of the curve can be. I don't know if I explained that very well, but I'll put a link down in the description to the Wikipedia page that will explain it much better than I can. But we're going to look at a 2, and then the 4 means it can be 40% back from the leading edge. So it's going to be 10% forward from the center line that curve is going to be centered upon, or that camber is going to be centered upon. So for a 10 centimeter wide airfoil, it's going to be 4 centimeters back from the leading edge is where that curve is going to be the greatest. And then for the last two digits, that is the percentage of the chord length that the airfoil can be thick. So 10% of 10 is 1 centimeter. So if we look at that, there we go. So see, we have a pretty much a flat airfoil. It's got a little bit of curve to it, but it's thin, it's relatively flat, it's got a little bit of camber, but not much. Real quick, guys, if you're enjoying this content, please hit the subscribe button. I'm going to be making more videos for this project in the future, and it really helps out when I know people are interested in it. I will be continuing this project just, for me, but if I see that there's interest in it and people are really digging the engineering behind it, that really helps keep me motivated to post videos and keep you guys in the loop. So if there's any other engineers or car nerds or any other kind of nerd or people that just enjoy this kind of thing, let me know. Hit the subscribe, drop a comment. Let me know if you want to see, different details of what's going on here, and I would love to share more about it. So thanks, guys. Back to the engineering. So on the other end of what I analyzed is an 8416. So that's got a lot more camber. It's centered still at the same spot, 4 centimeters back from the leading edge, and it is up to 1.6 centimeters thick for a 10 centimeter wide airfoil. I think I'm going to go with a 5-inch airfoil, 5 inches wide, but I'll get more into that in a little bit. So NACA 8416, you go upper, get into that mode, angle of attack, 0 degrees. And here you can see that we have a much curvier, much thicker airfoil, very voluptuous. And so that is an 8416. It's 1.6 centimeters, 1.6 centimeters thick. It's got a maximum camber of 8 millimeters off of the center line, so that means it's a lot more camber. And camber for airfoils just means how curvy it is. So this is a lot more curvy. So this is an 8416 NACA airfoil. So I just had a little, not cheat sheet, but a list of the airfoils that I wanted to analyze. So I wanted a 24, 44, 64, and 84. And then the last 2 digits I did 10, 12, 14, and 16. And I looked at a handful of them and kind of got the limits of what I thought would be good to analyze, because I had to, narrow down what I was looking at. And from my research, I found a lot of people use 4414, 4412, and I saw a few 6414 and 6416. So I was like, all right, let's get a few airfoils to either side of that to start looking at. So then I modeled them at 75 miles per hour. I decided 75 miles per hour because that seemed like the higher end of daily driving speeds, and I want this to be, suitable to keep on your car for daily driving, and I wanted it to provide as little drag as possible at those higher speeds, because we're already dealing with a lower powered car, and I didn't want to sacrifice any more power than I needed to. Here we can see I did a bunch of coefficient of lift over drag charts, looked at a bunch of different stuff, found some trends. Sorry if you can hear some noise in the background. We've got some vacuuming going on. And we can see some patterns coming out here, some data outliers. But here we have the 4410, or the 44 series. I modeled 10, 12, 14, and 16 here. And you can kind of see the changes that those airfoils undergo as you change the angle of attack. That's how tilted the airfoil is. And here you can see the 6400 series, and this kind of starts flattening out right here. And I did CL over CD because it's just kind of a metric of an idea of how efficient the airfoil is, like how much lift are you getting for how much drag you're getting. And so here I kind of modeled the averages of all the series, 24, 44, 64, and 84. And you can see that you get more coefficient of lift the more camber you have. You also get a bit more drag as well, which you can see here. So the 8400 series starts off at a coefficient of drag about 0.0115, and then the skinnier 2400 series starts off at 0.0058. So a lot lower, but you don't get as much lift either. So with all this stuff, I was like, all right, let's look at the 4464 and 8414 series. I did this spreadsheet and I got a lot of graphs. It didn't really tell me kind of what I was looking for. So other than that, like, a 44 or a 64 is probably going to be what I want to go with, just for a balance of the coefficient of lift to drag. But then I decided, okay, I need to figure out exactly how much drag and how much lift I'm getting. So I decided on 5-inch, 6-inch, 7-inch, and 8-inch width airfoils. I got the area in square meters right here, and I use those numbers to get the actual amount of lift and actual amount of drag that I get at 75 miles per hour. And so I just modeled the 5-inch and the 8-inch. because after I did a few, I realized like the 6 and 7 were almost exactly equidistant in between them. So it was evenly distributed. So I just plotted the two extremes, and you can see we were generating a lot of downforce at 75 miles per hour. Whenever you get up to about 15 degrees, that is the peak. And for an 8-inch airfoil of 2414, a NACA number of 2414 with 15 degrees of angle of attack, we're getting over 600 pounds of downforce. That seemed really big. So I was a little skeptical of that number, but everything else I was doing, all the simulations for all the other airfoils were consistent with that. So for the 4400, we top out around almost 700 pounds of downforce. That is an enormous amount of downforce for a 2,800 pound car. The 5-inch tops out around 423. I think that's a bit more reasonable. And then here we can see the drag for an 8-inch at the 15 degrees angle of attack. We're getting about 25 pounds of drag. That's not insignificant, but not as much as I was expecting either. For a 5-inch airfoil, we're only getting like 16 pounds of drag, which is very, very low. Or, I mean, it's lower than I expected. If we have the angle of attack at 0, we're only getting 3 pounds of drag for a 5-inch airfoil. That's not a lot. That's like a little extra headwind, you know? So here's another thing that I also thought was interesting. The 4400 had a unique characteristic that the other ones didn't have. So if you see right here, the downforce or the lift tops out around 670 pounds. And then it stays pretty consistent, only going down to about, what's that, 645? And so this looked really attractive to me because if you want to increase the drag in a braking scenario, you don't want your lift to just drop off because then you don't get consistent downforce. And if you're turning and slowing down and all of a sudden your downforce drops off, one of my dogs is going crazy for the vacuum cleaner. Anyway, and your downforce drops off, you could spin out easily because you're at the limit and then you're trying to brake and the active arrow is like, okay, trying to help you brake, and then your downforce drops off. It's just a bad time. Now we can correct for that in software and the control system where it's like, okay, don't go beyond a certain angle of attack or your lift's going to drop off. But if we can have an airfoil that can assist us in braking as well, that could be really, really handy. And if we want to maintain lift and increase drag in a high braking, high G turn, that could be really, really handy. So the 4400 series airfoil started looking really attractive. Here's the 6400. We do have a pretty sharp drop off after, let's see, at 13 degrees here, down to 20 degrees. So just a 7-degree change, you're going to lose about 100 pounds of downforce. That's not insignificant. So then we go down to the 8400, and then at 14 degrees to 19 degrees, that's just a 5-degree difference. We lose over or almost 150 pounds of downforce. That is an enormous drop off for a very small change in angle of attack. So again, I don't think we're going to want to generate 800 pounds of downforce for a GR86. So also, you have to keep in mind the structure required to keep the airfoil supported is going to get beefier and beefier the more downforce that we're generating. So I think a 4400 series, 4414 specifically, is going to be primo for our purposes. I also did a 4416. It's got a little... It's actually got a little less drag. It's got a little bit of a drop off here, but not as much as the 64. And then the 2400 has a little bit of a drop off, but it's got more drag, oddly enough. So I'm not really sure what's going on with the 2400, but I think the 4414 or the 4416 is what we're going to go with. So, yeah. So, I did more simulations for the 4414. And this time I did it at different speeds. And for the different speeds, I calculated the Reynolds number and the Mach number for each speed. And I used sea level, air density for generating the Mach number and the Reynolds number. So all the calculations are done in metric. I did change the end results to pounds for the forces just because my head thinks in pounds, but I like doing calculations in metric. I also used a 5-inch airfoil because I think the amount of forces we're getting with the 8-inch airfoil is much more than we need, especially if it's going to be a daily driver. I don't think we need to go with like an 8-inch airfoil. I think 5 inches is plenty, and so those are the numbers that I used for this, and I generated them at angles of attack between 0 and 30 degrees. Some of the simulations cut off around 23 degrees, but I think we start to get boundary layer separation around there anyway, so I wasn't really concerned about that. I don't think we're going to angle the airfoil much past 20 degrees, unless we're in a braking scenario, and then, you know, that's a different transient that we have to think about. So here is lift. Here is lift in pounds at different speeds. So down here, you know, what is this? 15 miles per hour. We're not getting a lot of downforce. 13 pounds. You speed up to 60 miles per hour and about 15 degrees angle of attack. We're getting 220 pounds of downforce. That seems like a lot for me, but I've never designed a spoiler before, much less active aero, or done really even a lot of airfoil analysis. So I'm learning this with you guys. Let's see, speed up to 90 miles an hour, we're getting 600 pounds of downforce at 14 degrees angle of attack. And then at 150 miles per hour, we're generating almost 1,800 pounds of downforce. That is insane, and I don't think building a structure that will support that much downforce is going to be useful. I mean, we're already probably going to have to reinforce the trunk as it is. I might not even mount it to the trunk. I'm not sure yet. That's going to come into play whenever we do the structural design. But one thing we can do is the faster we go, depending on how we build the structure, we can limit the angle of attack, and that way we don't get a downforce that we cannot, you know, support with our structure. So we can limit that in software and make sure that, like, hey, don't go, if you're at like 120 miles an hour, don't go above like 10 degrees angle of attack, or you're gonna freaking break the back of your car off. That's one thing we can do. And then here is the drag at different speeds. At 150 miles an hour, we cap out at like 370 pounds of drag. Again, that's going to be an insane demand on the structure for the type of car we're building this for. So again, one thing that we might want to do is limit the angle of attack for the different speeds. And we can generate a table that the control system can read from and adjust its maximum setting so we don't go beyond the limits of the structure. So I hope you enjoyed this video. If you want some more detail and a longer video where I go into, you know, more of the nitty gritty, I feel like I got pretty nitty gritty just in this one, but I wanted to keep it kind of, you know, high level, but still convey the information that I used to make the decisions that I did. But if you want something more nitty gritty and really go into all the detail, let me know down in the comments. I can do, you know, a separate video and like a director's cut version and nerd out about this a lot more. Let me know if that's something that you would like. I've also thought about doing a Patreon where I just post the videos where I actually do all of this stuff. I'll just record while I do this analysis and just kind of narrate and chat as I go through it. Also thought about starting a Discord for people that want to get involved in the project. If that also sounds interesting, let me know down in the comments. But for now, I'm just going to post these videos to YouTube and, you know, hopefully it'll catch on. If you enjoy this kind of content, please subscribe. I am going to be posting a lot more videos for this project in the future. I'm really looking forward to working on this and building something super, super cool. So thank you guys for watching. I hope you're nerding out with me. Be sure to be kind to someone today, and I will see you tomorrow. Peace.